Welcome back, students. So in this lesson, we are going to continue with the applications of differentiation. So we are going to learn the concavity and the second derivative test. So we are going to start with the revision first. Now in the previous lesson, we actually learned about the first derivative test. Now for the first derivative test, we actually use the first derivative, which is the dy dx, to find the relative maximum and the minimum point. So the f prime, the first derivative is actually the dy dx, and it is actually the slope of the curve. So when we have the f prime is positive, it means that the slope is increasing, the curve is increasing. And if we have the first derivative is a negative value, it means that the curve is decreasing. And when the first differentiation, right, the first derivative is 0, right, it means that the curve is actually horizontal line. Now, by using these three characteristics, so when the first derivative changing from negative value to 0, then to positive value, and we know that this point C is a relative minimum point. So on the other hand, if the first derivative changing from positive value to 0, and after that to negative value, so this curve changing from increasing to a horizontal line and then to decreasing. Therefore, we know that this point C is a relative maximum point. So this method is called the first derivative test. Now, in this lesson, we are going to learn the second derivative test and the concavity. So this is the three objectives of this lesson. Now the first one is to determine the interval on which a function is concave upward or concave downward. So what is a concave upward? Concave upward, it means that the shape of the graph is like this. So when the graph like this, we call it concave upward. Now, if the graph is in this shape, where increasing to decreasing, we call this concave downward, right? So we want to find the interval. Okay, what is interval? Interval refer to the value of x. So now when we have the x from a to b, we say this is the interval of x. So when we have a graph like this, we want to find out from what point to what point the graph is concave upward, and from what point to what point the graph is concave downward. All right, so this is called the interval. For example, right, let's say this is point A and this is point B. So we say from A to B, the graph is concave upward. Now the second objective is to find the point of inflection of the graph of a function. Right, we are going to talk about what is point of inflection later. And the third objective is to apply this method, the second derivative test, to find the relative extrema of a function. So let's start with the concavity. Okay, when we have a graph like this, we say this is concave upward. So now we can see here, all right, the graph is going from negative slope to positive slope. Okay, so in this case, right, when the graph is going from negative slope to positive slope, we say that f prime is increasing. The first derivative is increasing. Right, so we have to remember this, right? So when the f prime is increasing, then the curve will be concave upward. Now, when we have a curve like this, we say the curve is concave downward, and this happens when the f prime is decreasing, right? So we remember in this way, when the f prime is decreasing, right, the curve is concave downward. Right, now to explain this, let's use an example. Now for this function, fx equals to 1 over 3x to the power of 3 minus x, when we sketch the graph, right, we have this curve. Okay, so this curve represents fx equals to 1 over 3 x to the power of 3 minus x. Okay, now can you identify from what point to what point the curve is concave downward? All right, so this is when the curve is concave downward. So it happened from negative infinity to 0. So we can say this, right? The curve is concave downward on the open interval from negative infinity to 0. Okay, now why? When we sketch the first derivative, so we differentiate the f, 3 bring down, right? So multiply 1 over 3, we have 1, and the power minus 1, we have 2. Okay, so we have x squared minus, right, differentiate the x, we have 1. Now if we sketch the first derivative graph x squared minus 1 together with this, now we can see here when the curve is concave downward, the graph of the first derivative is decreasing. Okay, so as we mentioned earlier, so when the graph of f prime is decreasing, all right, so we have a concave downward. So on the other hand, let's consider where the graph concave upward. Now for this graph, the graph is concave upward, right, from 0 to infinity, right? So if we compare this graph with the graph of f prime, so we can see here, now when the f prime is increasing, the curve will have concave upward. Okay, so from here we know that when the f prime is increasing, right, the curve will have a concave upward. So this is what we need to actually remember. So when the f prime is increasing, the graph is concave upward, and the f prime is decreasing, the graph is concave downward. After we learn about concavity, we are going to continue with the points of inflection. So what is the point of inflection? The point of inflection is the point where the concavity of the function change. Now you can see here, right, there are 3 types of point of inflection shown. So for the first type, now the concavity change, right, at this point, right, before this point, right, the graph concave upward, And after this point, the graph concave downward. So this point is what we call the point of inflection. Right, the similar situation, right, for the second graph. So before this point, right, the graph is concave downward. So if we extend the graph will be actually something like this. Okay, so the graph is concave downward before the point, and after this point, the graph is actually concave upward. If we extend the line, so we can see it is a concave upward here. Okay, the third graph, right, this is the point, right, of inflection. Before this point, the graph is actually concave downward. Right, if we extend the curve, it will be something like this. And after this point, the graph will concave downward. Okay, so the point of inflection is the point where the concavity of the function change. So if we draw the line of tangent at this point, we can see that the tangent line is below the curve, right, at one side and above the curve on the other side. Now, to locate the possible points of inflections, right, this is what we do, right? We let the second differentiation be 0, right? The second derivative be 0. So please take note that this is the second derivative. Okay, so let the second derivative be 0, or the second derivative f double prime does not exist. So let's use the example to understand further. Determine the point of inflection and discuss the concavity of the graph of fx equals to x to the power of 4 minus 4x to the power of 3. Right, so first, this is the function we have. So to decide the concavity and the point of inflection, what do we need to do? We need f prime and f double prime. So we are going to differentiate 2 times. Now, after we differentiate, right, the first time, so 4 multiply 4 minus 1 is 3, and 3 multiply 4 is 12, 3 minus 1 is 2. And differentiate one more time, 3 multiply 4 is 12, 3 minus 1 is 2, minus 2 multiply 12 is 24, 2 minus 1 is 1. And this is the second derivative. So to find the point of inflection, what is the formula that we need to know? Okay, we know that point of inflection, f double prime, it has to be 0. All right, as mentioned here. So when we let this be 0, 12x x minus 2 be 0. So we will know that the x is 0 or the x is 2. Okay, so now these 2 points, that they are the possible point of inflection. So we are going to do some testing, right? So we can use a table where the x equals to 0 is here, and the x is 2, right, is this line. So we construct an interval, right? So we have negative infinity to 0, and from 0 to 2, and from 2 to infinity. After that, we choose one point from here. You can choose any point. For example, in this calculation, we choose x equals to -1, and we substitute into the f double prime here, right? Substitute into this equation. So when the x is -1, we get f double prime is positive value. Now, f double prime is positive value. This implies that the f prime is increasing. Okay, positive, right? This refers to the slope of f prime. So f prime is increasing, therefore the curve is concave upward. Now move to the second interval, right? When the x is from 0 to 2, we choose one point from here and we choose x equals to 1. Substitute into the f double prime equations, we get the answer is negative. So f double prime negative implies that the f prime is decreasing. So if the f prime is decreasing, so the graph will be a concave upward graph. So the third interval, right, we choose one point from 2 to infinity, and let's say we choose x equals to 3, substitute into the f double prime, we get the value is positive. So again, all right, this implies that the f prime is increasing. So when the f prime is increasing, then the graph is concave upward. So when we sketch the graph, right, so when we have from negative infinity to 0, the graph is concave upward. And from 0 to 2, the graph is concave downward. So we know that this point, when the x equals to 0, the concavity change from upward change to downward. So x equals to 0 is a point of inflection. Okay, it's a point of inflection. And for the point x equals to 2 here, all right, on the left-hand side, the curve is concave downward, and on the right-hand side, the curve is concave upward. And therefore, right, for this point, x equals to 2, the concavity change. So x equals to 2 is also a point of inflection. Right, so this is how we actually determine the point of inflection and the concavity of the graph. So from here, I want to highlight that we can actually remember this relation when the f double prime is positive, all right, it will be concave upward, and when the f double prime is negative, it will be concave downward. Okay, so also, right, from here, we can conclude that, all right, the dy dx, this is dy d2y dx2, the second derivative, when this is positive, all right, the graph will be like this, all right, concave upward, and this is the minimum point. And when the second derivative is negative, all right, so the graph will be like this, concave downward, and we have a maximum point. Now, however, all right, this theory is not generally true. So we have to use the graph to determine. Okay, so for example, when we have this graph x equals to x to the power 4, right, now if we find the f double prime, right, the second derivative is 0 when the x equals to 0. So let's try it. F prime is 4x to the power 3. F double prime is 12x squared. So when f double prime is 0, 12x squared is 0, so the x is 0. So we can get when the f double prime is 0, the x is 0. Now, however, at this point, if we sketch the graph when the x is 0, this point is not an inflection point because on the left-hand side, the curve is concave upward. On the right-hand side, the curve is also concave upward. the concavity does not change here. So this point is not the inflection point. So it is always better we actually use a table, all right, to confirm, right, whether is the concavity change at a certain point. All right, so right, this is how we actually determine the point of inflection, and by using the second derivative test, we can actually find the concavity of the graph. The second derivative test. Now, in the previous discussion, we know that, all right, when the second derivative is a positive value, so this is equals to second derivative d2y dx2. This is a positive value, right? The graph is concave upward, and we have a minimum point here. All right, so the point is minimum, relative minimum. And when we have the second derivative is a negative value, this equivalent to the d2y dx2 is less than 0. So we have concave downward, right? The curve is concave downward, and the point here is the relative maximum point. So we are going to use these two characteristics to actually help us to test the function, right? We call this the second derivative test. Now, so the second derivative test say that if the f is a function such that, right, the first criteria, the first derivative must be equal to 0, and the second derivative of f exists on an open interval containing c, it means that, all right, the second derivative exists at this point, and if the second derivative of this point is a positive value, then this point, the c, right, CFC is a minimum point, relative minimum point. And if the second derivative is a negative value, right, so this point is a relative maximum point. So this is the second derivative test. Now, if the second derivative at this point equals to 0, right, then this test fails. Okay, so we cannot tell whether this is maximum or minimum, right? So f may have a relative maximum, a relative minimum, or neither. In such case, you can use the first derivative test to see if, all right, this point is actually relative maximum, relative minimum, or neither. Okay, let's consider this example. Example 4. Now we are using the second derivative test to find the maximum point or the minimum point of this function fx equals to negative 3x to the power 5 plus 5x to the power of 3. So as you know, to use the second derivative test, again, we need to differentiate for 2 times. So we differentiate the first time, right? We have 5 times 3, 15, negative 15x to the power 4, and 3 times 5, 15x to the power 2. All right, so this is the first derivative test, sorry, the first derivative. And after that, we differentiate another time. So we have the second derivative, 4 times 15 is negative 60. 2 times 15 is 30. Okay, now we know that, right, according to the second derivative test, first we need to find the f prime equals to 0. Okay, from here we want to find what is the value of x. So we factorize this, right? Take out the 15 and take out the x squared. All right, so we have 15x squared, and of course this is 1. After we take out 15x squared, this is 1, and this will be negative x squared. So we have 1 minus x squared. So when the f prime is equals to 0, So 15x squared 1 minus x squared is 0. And from here we can find the value of x. The value of x is 0, or 1 minus x squared is 0. Okay, so if 1 minus x squared is 0, so the x will be positive negative 1. Okay, so right, f prime equals to 0. We have the possible value of x, negative 1, 0, and 1. Right, so the other critical points of f. Now, after that, we need to use the second derivative test, or we say apply the second derivative test on this value to see if they are maximum point or minimum point. Okay, so negative 1, 0, and 1, we put this on a table. Okay, so this point here is negative 1, and this is 0. Okay, point here, x equals to 1, negative 1. Okay, and if we substitute into the function fx here, we get the y is negative 2. And when the x is 0, of course the y is 0. And when the x is 1, substitute into the function, that y is 2. So we are going to apply this into the second derivative, right? So we are going to take this one, the second derivative, 30x1 minus 2x squared. So when the x is 1, when the x is negative 1, the second derivative, right, we have 30, negative 1, 1 minus 2, negative 1 square, and this gives us positive value. Okay, the reason is this is negative 30, okay, and this is negative 1. All right, so we have 30 here. It's a positive value. So this positive value tells us that this point is a relative minimum point. We continue to test the second point when the x equals to 0. Substitute into the f double prime. So we have 30 multiply 0 multiply 1 minus 2, 0 square 0. Now, since this is 0, so when we multiply, we get the 0 for the whole term, and we get, all right, f double prime is 0. So in this case, the test failed. All right, so we don't know whether it's a relative maximum or minimum. Now, however, we can move on to the third point when the x is 1. So when the x is 1, right, the second derivative will be 30 times 1, 1 minus 2, 1 square, and this gives us 30 multiply negative 1, and it's negative 30. So the second derivative is less than 0. Now when the second derivative is less than 0, now we know this is actually a maximum point, and the graph is actually concave downward. Okay, so and this is the minimum point. Now we can actually use this information to sketch the graph, right? So okay, now at this point, right, because the second derivative test failed at this point, you can use the first derivative test and observe the f increases to the left and right of this point. Okay, so if we use the first derivative, right, the f prime increases, the slope increases from on the left and on the right. So this is actually an inflection point where, right, the curve is concave downward before 0 and concave upward, okay, concave upward after 0, okay, concave downward before 0 and concave upward after 0. So this point is an inflection point because the concavity change. Right, so if we sketch the graph, right, we have this point, -1 and -2. Let's refer -1 and -2 here. Right, the graph is actually concave upward. It is the minimum point, so we can actually draw the curve like this. Okay, and right, at this point, right, the test failed. Right, we use the first derivative test to determine it is the point of inflection. And for this point, 1, 2, right? So we know that the second derivative test is negative, right? We have concave downward. It's a maximum point. Okay, it's a maximum point. So actually the graph is this. Okay, so this point is neither a relative minimum or relative maximum, right? So, and the graph is actually like this. So this concludes the second derivative test, right? So remember that, right? The second derivative test, we only perform this after we have find the first derivative and let it be 0. Okay, so let the first derivative be 0. Find the value of x. After that, use these values to perform the second derivative test to determine whether they are the relative maximum point or relative minimum point. Right, now, of course, we can also use this f double prime equals to 0 to locate the possible inflection point. And to confirm this, we can always use the first derivative test.